Okay, started putting together the electrochemistry videos for flipping this class, and looks like I think I can shove stuff into 3 more videos, including this one. So the end is nigh, folks. All right, so I'm looking at sections 17.1 through 17.2 here. So go ahead and read those if you have not, and then let's get into how this stuff is going to work. Thinking about some background material. So I don't know how much to assume y'all have had in terms of physics. Probably the best assumption is not much, but I hope it's not too bad to try to catch you up on that. So if we were in class, the way I would do this, I would say, well, look, let me hear from y'all what you think the idea of electrical potential means, and try to lead you to the idea that the potential is kind of, a lot of people think of it like hydraulic potential, like where you have a dam with water built up behind it, and you have a head potential because of that. So you can think of it the same way, but it's not water, it's like electron density build up on one end. Now you can think of this like a battery, so that you have an electron dense area and an electron poor area, and therefore you have a gradient across that, or a potential difference. We'll measure potential difference in voltage. That's probably fairly intuitive to you at this point. Then I want to ask, what is electrical current? And I think there's a lot that goes on with this, and some controversy about which direction you measure current flow in. But to be agnostic about it and just say that electrical current is the flow of electrical charge. That way I've said it that way so that I can think of it either direction. A lot of times in physics, you will think of electrical current flow as moving from positive to negative. Usually, in terms of chemistry, we're going to think of it the other way around, as if the flow is from a high negative potential towards a positive potential, because usually we think of the electrons as being what's actually moving. Like in a wire, it's electrons that move. Now, technically, you can move current, you can move the charges with positive ions also, but then you got to get into dynamics of flow and stuff like that, and electrons, you get to ignore that, which is nicer. One final one there is conductor versus insulator. So if you have, let's say, an electric fence, right? You have an electric fence, and you have 2 options of what to pick up that electric fence with. You can use a piece of metal in your hand, or you can use a piece of wood in your hand. Well, which one is going to give you a shock and which one isn't? The piece of metal we think of as a conductor. You will get a shock. The piece of wood we think of as an insulator, and you will not get a shock. And why is that? It has to do with how easy it is for that material to conduct electrons. And if you look back to your Gen Chem 1 stuff, very end of Gen Chem 1, at least in the case of the way I did it last, or when I did it last, you have the idea of molecular orbitals, MO theory. And so when you have these blended molecular orbitals, it's very easy for an occupied molecular orbital that's high in energy, highest occupied molecular orbital, to move electrons along. Or if you have a very high unoccupied molecular orbital, it's easy for charges to move into those. But it has to do with what's occupied by the electrons and what isn't. All right, so now electrochemistry. Electrochemistry is where we're talking about energy still, right? But we're talking about moving energy from a state of electrical energy to a state of chemical energy or potential. And so the bridge between those is the electron transfer and what's going on with the electrons. Protons are going to stay nice and neat in the nucleus with the positive charge, so they're not going to do much absent nuclear chemistry. Neutrons they don't have any charge, so they're not going to play. That leaves your electrons, which are out there in the cloud, and they can transfer from one chemical species to another. This electron transfer is the electrochemistry. So we can actually measure current flow. So I hope you saw back in Gen Chem 1 the idea of base units and then composite units. Like a meter is a base unit, but a velocity like meters per second is a composite unit because you're stapling two base units, the meter and the second. You're stapling those together to make a composite unit. But we don't have one for flow of charge, current. So the amp is one of the very, very few base units defined in the metric system. So the amp is this many this many moles of electrons, this much coulombic charge flows. So each one electron carries 1.602 e neg 19 coulombs of charge, and that's an amp second. So think of electrical current flowing in closed paths like a circuit. I'm going to draw some of those out at the end of the presentation here. And the potential. So the SI unit for potential is the volt. So voltage. So we practiced balancing oxidation and reduction reactions. So now we're going to define some terms. Oxidation is the loss of electrons. The electrons fall off of some species, and the charge and the species becomes oxidized. I want to actually add to this here. So ox state hard to write with a mouse increases, e.g. for example there. So Fe0 to Fe2+. So look at my charge there. What happened to my charge? My charge went from 0 to 2+. So the charge went up. That is oxidation. All right. So now we're going to do the opposite down here, and we're going to say that the gain of electrons. Right? Oh, I should have put here. Let me put. No, that's not a color you can see. Plus 2 electrons. See, the electrons used to be here on the Fe0, and they fell off. So now you've got Fe2+ and 2 loose electrons. But down here we could say the opposite. I'm just going to write the exact opposite. I'm going to say Fe2+. You could take those 2 loose electrons, 2e-, and staple them on, right? And so now you go to Fe0. So look at what happened to your oxidation state of your charge. Up here in the red, it went from 0 to 2+. Charge went up, it's oxidized. Here it went from 2 positive down to 0. That charge was reduced. We call that reduction. It is a gain of electrons, but we're talking about what happened to the oxidation state. The oxidation state was reduced. So oxidation and reduction always happen together. You're not allowed to have any free electrons running around in your reaction, in your solution. because that electrocutes people. Yeah, and so the terminology can get a little confusing here. So when a species is reduced, right? When something gets reduced, there must have been something causing that. And the thing causing it we call the reducing agent, or some people use the term reductant. And if something gets oxidized, there must be something causing that, something causing it to become oxidized. We'll call that the oxidizing agent. But here might be a source of the confusion. So an oxidizing agent, since it's causing something else to get oxidized, it in turn gets reduced. And a reducing agent is causing something else to get reduced, so it is therefore oxidized. And then they'll be on the reactant side. Okay, so oxidation number or oxidation state. So this is really accounting, okay? So we're just trying to figure out where all of our electrons are. So we're going to try to assign oxidation states to things so we can tell what's being oxidized and what's being reduced. And it's all about the energy of where these electrons are. So you've seen these rules before. Just reiterating again, for elements of monatomic ions, the oxidation numbers are just whatever the charge is. Could be 0. So whatever that charge is your oxidation state. For elements and for monatomics, so things that are just by themselves, just iron, or just sodium, or whatever, or just oxygen we've used a lot of times. O2 by itself is just oxygen. So those are just the charge. And then, so this gets into a little bit of semantics. So the oxidation numbers, they're not real charges necessarily. So in the practice problem where we did methane, CH4, well, the carbon doesn't have an actual -4 charge on it. It just acts like that in the oxidation reaction, because if it had an actual -4 charge on it, then we would need to call that an ionic bond, and it isn't. It's still a covalent bond with the C to the H. They're still sharing 2 electrons between them. It's just how we're doing the accounting to make it work. And so there's certain rules for assigning these oxidation numbers that we played with, right? So generally, oxidation numbers are going to be small whole numbers, but they don't have to be. Especially when you're dealing with carbons. It is okay to have fractional oxidation states. That might come up in Orgo for you. Definitely comes up in the environmental chemistry field when we're talking about a lot of partially reduced or partially oxidized organic chemicals. So when we change that oxidation state, right? So this copper is 0 because it's just copper by itself in a metallic state, and it goes to 2+. Let me see what happened to my charge here. It went from 0 up to 2+. I'm going to call that oxidation. And when you have oxidation, you've got to account. See, where did these 2 electrons used to be? They were on this copper, and they fell off. And so you've got a copper 2+ plus 2 electrons. So notice that everything on the left side, on the reactant side, is accounted for. On the product side, everything's still there. It's just now that they're separated. Reduction is exactly the opposite. You can take something with a higher oxidation state and go to a lower oxidation state, a +1 here down to a 0 on the right, and that's a reduction. A decrease in the oxidation number. So reduction is a decrease. So your steps for balancing these guys, assign some oxidation numbers, then do the half reactions, an oxidation side and a reduction side. They always come together. You balance each of them. And then step 5 here says combine them so that the electrons cancel out. You remember that if you have 8 electrons getting consumed on the reactant side, you've got to have 8 electrons on the product side. So you've got to multiply so that you have the same number of electrons falling off as being stapled on. It has to be equal. Now the other rules still exist. You still have to balance atoms, and you still have to balance charges, everything else. Okay, so we can envision a reaction where you take, here's copper metal, right? And you stick it in this test tube. I guess the test tube might be visible in the video. I hope so. That's a test tube with a solution in it. And what they're trying to show here, this, again, is from your textbook. And they're trying to show I think this is a silver nitrate solution, but you don't care about the nitrate because it's just a spectator ion. All you care about is that there is dissolved silver 1+ in this solution right here. Okay, so now what you're going to do in step B, you're going to take that copper wire and you're going to stick it down in this silver nitrate solution. Look, there's just a spontaneous reaction that occurs, and you have silver ions being reduced to metallic silver on the surface of the wire, and in their place where there were silver ions in the solution, copper is coming from the 0 valent copper on the wire. It's being oxidized to copper 2+, and you can see it happen because you get this blue color. It looks kind of green on there, but usually it really is a blue color when it comes off. So you get dissolved copper 2+ ions in the solution. So you can see how this could run directly in a test tube, right? But what if we took the 2 parts of this reaction and did them in separate containers, separate cells, let's call it, and looked at it that way? So it would look like this. So what's happening here, we've got, here's our silver Ag+ and our nitrate solution. Now over here, we could just consider this to be a water solution to start with, or whatever you wanted to here. Or you could have copper nitrate to start with. It doesn't really matter, because what's going to happen is, remember our reaction was that copper was becoming oxidized. So copper is falling off of this metallic copper strip and turning into copper 2+, right? Now, what's happened to its electrons? Well, the electrons in this case are able to flow up the copper through a wire and get over here to the other part of the cell where there's some silver+ ions that can absorb those electrons and become silver metal plated onto this electrode. And you can actually make pure silver this way. So in principle, you can do this with any spontaneous, y'all know what that means now, spontaneous reaction, right? You can do it, and you can extract electrical energy from it. So that cell is designed so that the electrons flow up that wire and out, and in that flow of electrons, that's electricity. So the oxidation reduction half reactions, you put them in different compartments like that. And we're going to get into some more definitions in a second with the oxidation and the reduction, which cathodes. But the moving electrons are important as a source of electricity. So I wanted to devote a whole slide to this definitions-wise. The definition of the electrodes is slightly different in chemistry than it is in common practice, like if you were to take an electricity course, like a wiring course or something like that at tech school. The definitions can sometimes conflict. So, For chemistry purposes, let's define it really clearly. What we're going to call the anode is where oxidation happens. What we are going to call the cathode is the place where the reduction happens. And I'm about to go back to the cell and show you on it too. All right, here's our cell again, right? So I'm going to call this the copper anode. Why am I calling it an anode? Because that's where oxidation is happening. I'm going to call this the silver cathode. Why? Because that's where reduction is happening. Okay? And then you can see that when we set this up, look at this, we can actually measure, you can actually just attach a voltmeter to this thing, and you can measure a voltage. You've got a solution here, you've got a solution here with the cathode. You don't have to do anything else to this. Just having these two solutions connected by this wire creates a voltage. We can extract electrical energy from the chemistry. And so you got, this is the same thing you just said. We got the copper metal anode, that falling off, letting the electrons go. Those electrons moving, that's what gives you this, in this case, 0.46 volts. Here's the reaction that's happening at the cathode. Now, we know it's a cathode because oxidation is happening, but it's the same reaction we talked about a while ago. The copper metal is becoming copper 2+ ion and loosing those two electrons. Those electrons flow through the wire to the cathode. And then at the cathode, you have reduction. You've got loose silver plus ions in the solution that are getting plated onto the silver electrode as solid silver. This is the same reaction that we did in the test tube earlier. It's just now that we have it separated by this wire to make it work. And then notice that there is that thing called the salt bridge in between. And then in the salt bridge, what we're doing is we're making sure that charge balance works. So as you're creating these copper 2+, suddenly we have new, and we're extracting the electrons. The negative charges are flowing up and out that wire. So we're creating new positive charge in that solution. We've got to balance the charge in that solution. And the way they're doing it in this diagram is using a nitrate salt, so that the nitrate can provide negative charges to balance the positives, and the counter ion can, it's was it sodium nitrate, or I think it was sodium nitrate they used in that. I'll go back to that image in just a second. So that the sodium can provide the counter charge where the cations are being plated onto the silver electrode. So that enables neutrality to be achieved, and you have current flow in the wire above. So here's the diagram again, just to reiterate all that. So as the copper metal, 0 valent, is releasing the 2+ ions, we've got to have 2 NO3- ions come out of the salt bridge to keep our charge balance neutral in this solution. As positive ions are plating onto this, we're losing positive charges in our solution, so we're going to lose some negative ions into the salt bridge also. Or you could say you could bring sodium out. Either way, as long as you keep the charge balance consistent. Okay, so cell notation. Let's look at the way this works. I'm going to try to draw it out for you as we go here. So it's kind of a shorthand for what happens. So we're going to put our oxidation on the left. Let's see, what does this first piece here say? It says copper. All right, so what I'm going to do is I'm going to start with my copper, right? And I do want to put states. So we're going to say it's a solid, right? Okay, cool. And then we're going to separate, we'll get to the silver in a second. We're going to separate with a vertical line a phase boundary. So remember that solid copper is different. It's a different phase from our copper 2+, right? So that's what that solid line I just drew, because this phase is AQ, aqueous, right? All right, cool. So then, so that's our single vertical line to separate the different, should have said aqueous in there too. And then we're going to need, well, where's our salt bridge? So this kind of thing, I'm going to draw a big double line. I tend to, oh, that's terrible, but it's a double line. I'm going to erase it and do it again. Try it again. So it's a double line. I tend to draw it a little bigger than the solid lines. I don't know if that's just me being old or what, but I like for it to be just a little longer, extend above and below, right? And then on the other side, what's happening? Well, you've got silver, right? That's aqueous. And so we have another phase boundary, right, to silver solid. You know that silver solid is going to be a 0. Copper solid also going to be a 0, but you do need to show the charges for the ones that are aqueous. So let's see, what else do we need to solve? Oh, yeah, we got that, right? We did not include anything like the nitrates or anything like that. They're just spectator ions. So when you look back, again in Gen Chem 1, we talked about net ionic equations, and this is where net ionic equations really come into play. So you don't have to put the spectator ions in. Let's see, we've got a copper. That's the oxidation. Y'all remember why it's oxidation? Because the charge went up, because the oxidation state went up, and the oxidation state went down, reduced for the silver. So oxidation on the left, reduction on the right. Okay, so summarize this. We've got galvanic cell summary, and it's talking about the same reaction we started with the single test tube. We're compartmentalizing that into different parts in order to extract energy from it. And so if it is jumping up in your head that we're taking this oxidation at the anode, reduction at the cathode, making the electrons go through this wire in order to, this starts to look like something that we would call a battery. And you are absolutely correct. This is indeed how a battery works, and we're going to get into that in a little more as we go forward. Well, that's how our galvanic cells work. And so next we're going to get into standard reduction potentials and how these cell potentials work. So section 17.3 is going to be the next video, and we're going to talk about how we're going to calculate or figure out otherwise with these cell potentials what's going on and what to expect from any battery that we might make.